Hi, this lesson is all about how we can understand the geology of Mars, how we can actually put together this image that you can see on the screen at the moment. This is a geological map of Mars produced by the United States Geological Survey. I've put a link to the internet site where you can find this and find out more about it in the extension part of the lesson guidance. But the question we need to answer is, how can we work this out? We've explored a tiny part of this using some of the Mars rovers. So how can we confidently put together a map like this that shows with the different colours the different rock types that we can find on the surface of Mars? To do this, we need to look at a couple of different types of data. There's two preparation videos that you should have watched already. One on the Mars Global Surveyor and the other on meteorites. If we think about the Mars Global Surveyor, this was a NASA mission that ran from the late 1990s through to the early 2000s. It was a satellite whose job it was to map the surface of Mars in more detail than had ever been done before. Now, as well as surveying landscape features, or Marscape features, I suppose, of the Earth's surface and plotting their different elevations, it was also looking to record the infrared signature of the surface, because different minerals and different rocks will emit different amounts of infrared radiation. So we could come up with a map showing us these changes in infrared emissions. But that on its own isn't going to tell us necessarily what the geology is. We need to be able to link those emissions to the type of minerals that we find in the rocks. And to do that, we had a very useful clue. The image you can see here is a slice of the Zagami meteorite, the biggest ever Martian meteorite. One afternoon, on 3rd of October 1962, a farmer was out chasing crows away from his cornfield in Nigeria. There's a loud bang, buffeted by a pressure wave, and about 3 meters from him, there was a hole in the ground with this big lump of rock. This rock weighed 18 kilos and is the biggest piece of Mars that we have. Now, by using this meteorite and analysing this meteorite, it's possible to look at the minerals that are in it. And crucially, using this meteorite, it's possible to work out what the infrared emissions are from the different minerals that we find within it. You have this graph on page 18 of your Theme 2 booklets. What I'd like you to do is I'd like you to compare the emissions from the Zagami meteorite, which you can see is the top curve, with some of these common minerals that we can find in, well, most rocks. We're going to look at exactly what these minerals are in more detail in Theme 3. But what I want you to do is I want you to compare the high points and the low points from the Zagami meteorite and see if you can work out which minerals we might find within it. Press pause now and have a go at the questions on page 18. Okay, let's have a look at this graph and perhaps what we've worked out. First thing I should say is it's not particularly easy. This is a complicated graph. And when we look at the Zagami meteorite results, we need to remember that they're a combination of the emissions of the different minerals that we find within the meteorite. Let's have a look at comparing perhaps some of the main low points from the Zagami meteorite emissions. If you look at the blue line, this also shows us perhaps a high point. From this then, can we work out which minerals are the best match? Now when I look at this, I see a really good match with one mineral in particular, and that's aurgite. You can see the low points of the Zagami meteorite match the low points of the aurgite curve. That clearly is going to be the mineral that makes up the bulk of that meteorite. But it's not a perfect match. There are some other minerals that seem to have an influence as well. The second one I can see is hornblende. The larger wavelength there, you can see on the right hand side, it matches that low point on both the meteorite and hornblende. Similarly, the high points on the blue line match hornblende and aurgite. The final mineral that I think is represented, and this is perhaps harder to recognise, is olivine. You can see a relatively high point at about 16 microns along the blue line. And you can see it starting to decrease at 9 microns along the red line on the left hand side. But I think there's going to be a lot less olivine than the other minerals. When we go on to theme 5 and we start looking at igneous rocks, we'll be able to link those minerals to a particular type of rock we describe as being mafic or even ultramafic. That word will make more sense in year 10. Okay. Have a go at the digging deeper activity. How can we use this type of information to make a geological map of Mars? What can we actually do? How can we put this data together? Next time, we're going to start trying to tie all of these ideas together and see if you can come up with a good interpretation of one of the biggest features that we can find on the Martian surface.